In this presentation, I'll be explaining how field effect transistor or junction field effect transistor can be used as a voltage controlled resistor and its application, and also I will be explaining one problem in the voltage divider biasing. Let us see voltage controlled resistor. One of the most common application of a junction field effect transistor is as a variable resistor whose resistance value is controlled by the applied DC voltage at the gate terminal. That is, by controlling the gate to source voltage, we can control the resistance between source and drain. It is working as a variable resistor. Now, coming to the drain characteristics of this JFET, if the VDS is less than the pinch of voltage, as we see in that one, that will be the variation of VDS versus ID is a straight line. This has been plotted VDS versus ID for different VGS when VG equal to 0, when VGS equal to different values, and this is the variation of VDS versus ID. And this region is called the ohmic region, in which the resistance of source to drain resistance is varying as gate to source voltage is changing. Therefore, this is a ohmic region that when it is used as a variable resistor, it is made to work in this ohmic region, and when it is used as an amplifier, it will be working in this active region. And if you see this one, the drain to source resistance increases as the gate to source voltage approaches the pinch off value. Gate to source voltage maximum value of VGS is equal to VP. For example, if VGS equal to 0, the corresponding variation, that is, this is actually magnified version of this ohmic region. This has drawn the magnified version of this ohmic region, in which when VGS equal to 0, it is having a slope of certain value of the slope. For example, it may be 100 ohm. Or this is the resistance offered between source and drain when VGS equal to 0. Similarly, as VGS value increases, we can see that when the slope is increasing, or we can say that resistance is increasing. As such, here the resistance between source to drain is increasing as the gate to source voltage increases. Maximum value of gate to source voltage is the pinch off voltage VP. Therefore, as an example, when say VGS equal to minus 1.5 volt, you can calculate what is the resistance that is equal to resistance between drain to source. That is equal to, we can say that what is the slope of this one, or in that one we'll be getting it is equal to 444 ohms. Similarly, as VGS is increasing to say minus 2 volt, that is the resistance is increasing to 800 ohms. Like that one, VGS can be made to minus 2.5 volt, and correspondingly it is equal to 3.3 kilo ohms. Therefore, by changing the gate to source voltage, you can vary the resistance between source to drain, or it is acting as a variable resistance if the voltage VDS is less than the pinch off voltage. Therefore, that is called voltage control resistance operation of a JFET. That is, in the ohmic region, it is working. It is working as a variable resistor. Continuation of voltage control resistor. As the voltage between gate to source is changing, the resistance between source to drain is changing, or it is working as a variable resistor. Now, the relation for drain to source resistance, RDS equal to R0 divided by 1 minus VGS divided by VP whole square, in which the R0 is the resistance between drain to source when VGS equal to 0, or R0 is the resistance between drain to source when VGS equal to 0 volt, and assume that R0 equal to 100 ohms. That is, we are assuming that when VGS equal to 0, the resistance between drain to source to drain, it is equal to 100 ohms, and VP equal to pinch off voltage, we are assuming it is equal to minus 3 volt. Now, applying this equation, you can get it as the equation for RDS equal to 100 divided by 1 minus VGS divided by minus 3 or whole square, or 100 divided by 1 plus VGS divided by 3 whole square. For different value of a VGS, if you substitute, you can get what is the resistance between drain to source. As an example, when VGS equal to say minus 0.5 volt, if you substitute it is equal to minus 0.5, you will be getting it is equal to 144 ohms. Similarly, if you for different values of VGS, you can substitute like VGS equal to minus 1 volt or minus 1.5 volt. If you substitute, it will be getting it is equal to 400 ohms. Therefore, as you change the gate to source voltage, the resistance between source to drain is changing. For example, in this case, VGS equal to 0, it is equal to 100 ohm. When VGS equal to say minus 1.5, it is equal to 400 ohm. It is the source to drain resistance is varying as gate to source voltage is changing. So it's like it is working as a variable resistor. That is in the ohmic region, JFET is working as a variable resistor, or that is controlled by voltage. That is why it is a voltage controlled resistance. By changing the voltage between gate to source voltage, you can vary the resistance between source to drain. That is called voltage control resistor. Coming to the application of a voltage control resistor, as you see that one, we can say a operation amplifier. It's called the inverting operation, non-inverting operation amplifier. Of course, you are giving the input to the non-inverting input. That's why it's called non-inverting amplifier. And this signal is being amplified by certain magnitude. This is the input signal, and this is the output signal. And the relation between output to the input voltage, that gain is equal to, actually it is equal to 1 plus RF divided by this resistance R. So 1 by RF plus R1, or that resistance, that is called the gain of the amplifier. Therefore, in order to vary the gain, feedback resistance you are not disturbing, you will be changing this value of this resistance R1. Therefore, 1 plus RF divided by R1 is the gain of the amplifier. By changing the value of the R1, you can vary the gain of this amplifier. Therefore, here the voltage, by using a voltage controlled a JFET, the drain to source resistance can be changed. Therefore, we are connecting a JFET in the it is made to work in a ohmic region, in which by controlling the gate to source voltage, you can vary the resistance at the input side. That we are changing the resistance at the input side, so that gain of this inverting amplifier 1 plus RF divided by R1, that R1 is being changed, thereby the gain of the amplifier can be changed. Therefore, you can use the JFET in ohmic region as a voltage control resistor, and that can be used as a variable resistor in the case of a non-inverting amplifier using a operation amplifier. Therefore, that is the one application of a voltage control resistor for voltage amplification using operation amplifier. The previous presentation, I already explained different biasing techniques of junction field effect transistors, and which we have been concentrating in fixed bias and self bias, as well as voltage divider biasing. This type of biasing is widely used in voltage divider biasing. Coming to that one, fixed bias, what we do is, he will be applying a constant voltage VGG is applied. A reverse biasing voltage of VGG is applied at the gate to source junction. Therefore, if you write the corresponding Kirchhoff's voltage law equation to this loop, you will be getting it is equal to VGS, gate to source voltage VGS equal to minus VGG. If you write the loop equation, minus VGG. Okay. Now here again, if you draw the variation of VGS versus ID, that is as per the Shockless equation, that is ID equal to IDSS into 1 minus VGS divided by VP whole square. That is the Shockless equation relating the gate to source voltage and the drain current in a junction field effect transistor. Now that is this exponentially decaying curve, which is equal to ID equal to IDSS into 1 minus VGS divided by VP or square. And to find the operating point, you have to calculate what is the gate to source voltage VGS, and from this equation you can see that VGS equal to minus VGG. Therefore, corresponding to minus VGG, you draw a line parallel to this y-axis, and this point of intersection is the corresponding IDQ that is the corresponding Q point drain current. IDQ will be getting corresponding the point of intersection of the this also called transfer characteristics and this point. That is the operating value of the drain current. And in order to calculate what is the VDSQ, that is operating value of drain to source voltage, you have to write an output loop equation. In that one, VDD equal to ID into RD plus VDS, or VDS equal to VDD minus ID into RS. From this one, you can calculate what is the drain to source voltage at the operating point, and this is the corresponding drain current. That is operating value of the drain current, IDQ, and you can substitute in that one. You will be getting VDSQ. That is in the case of a fixed bias. Now coming to a second one, self bias. Rather than applying a voltage, negative voltage here, that is derived by connecting a negative voltage reverse biasing derived by connecting a resistance in series to the source. RS you are connecting like this one. Now again, if you apply the Kirchhoff's voltage law to this loop, you will be getting VGS equal to minus, if you write this loop equation, minus ID into RS. VGS equal to minus ID into RS. Again, coming to the Shockless equation relating the transfer characteristics, it is the transfer characteristics of the JFET. And when you are connecting an RS like this one, corresponding VGS is given by minus ID into RS. And this is a straight line equation, and you are plotting that equation, that is VDS was VGS equal to minus ID into RS, and with a slope of RS, you are drawing a straight line here, this one, this equation, and this point of intersection is the operating point that corresponds to the operating value of the drain current, IDQ. And in order to calculate the corresponding VDSQ operating point, again you can apply the Kirchhoff's voltage law equation output loop, that is equal to VDD equal to ID into RD plus VDS plus ID into RS, or VDS equal to VDD minus ID into RS plus RD. From using this equation, that is, you will be getting IDQ from this point, IDQ. Substitute that IDQ in this equation, then you will be getting VDSQ. Like that, you can find out the operating point. The third one, what is widely using, is the voltage divider biasing, in which, as you know, that one input side you will be connecting two resistors, R1 and R2. At the midpoint is connected to the gate terminal. And again, the voltage at this point is given by VDD divided by R1 plus R2 into R2. That is represented as here VG. And again, if you write the Kirchhoff's voltage law to this loop, you will be getting VGG. We applying this Kirchhoff's voltage to this loop. VGS, that is gate to source voltage, is given by VG minus whatever the voltage coming here, VG minus ID into RS. Then again, coming to this transfer characteristics of this one of JFET, that is Shockless equation, ID equal to IDSS into 1 minus VGS divided by VP whole square. And now to find out the operating point, you have to find out that whatever they drawn, these are called biasing lines. This is the biasing line in the case of fixed bias, and this is the biasing line for the self bias. And in order to draw the biasing line, this is called the biasing line, and you have to draw a straight line obeying this equation, that is VGS and ID. And that will be getting as this one, and you will be getting, this is the, when for example, when ID equals 0, you can get what is VGS. That is, when ID equals 0, what is VGS? We'll be getting it is equal to whatever this voltage VG, that is VDD divided by R1 plus R2 into R2. That is this voltage. Similarly, when VGS equal to 0, you can calculate. When ID equals 0, you can calculate what is the VGS. Like that, when you can draw this bias line, and this point of intersection corresponds to the drain current at the operating point. Once you calculate IDQ, you have to write the output equation, which is equal to VDD equal to ID into RD plus ID into RS plus VDS, or VDS equal to VDSQ. Q point drain to source voltage equal to VDD minus ID into RS plus RD. From this equation, you can calculate what is the drain to source voltage at the operating point. Therefore, this is the three biasing techniques used in the JFET, and this is the way how which you can calculate what is the operating point corresponding to different biasing lines. Then now let us consider a problem on voltage divider biasing. I should know this is widely used in biasing technique, in which JFET and channel JFET is these are the biasing resistors R1 and R2, and the midpoint is connected to the gate terminal, and there are resistance in series to the source as well as drain RT. And this is a fixed biasing circuit in which the question is that determine the following for the network, in which you are asked to find out what is the operating point value of drawing current IDQ and VDSQ. Then what is VD? What is the voltage of drawing voltage with respect to the ground? And what is the voltage of the source with respect to the ground? And what is the voltage VDS corresponding to that one? And here it is equal to IDQ and VGSQ, and here corresponding VDS, and also here it is equal. These are the question. Let us see first one. What is first? As per the Shockless equation, as you know that one, ID equal to IDSS into 1 minus VGS divided by VP whole square. Now in this equation, all you have to substitute. This is the Shockless equation. When VGS equal to 0, what is the ID? As per Shockless equation, drain current ID equal to IDSS into 1 minus VGS divided by VP whole square. This is the pinch off voltage that is given as minus 4 volt, and IDSS is given as 8 milliamperes. And you can plot a curve between ID and VGS. That is what it is called that transfer characteristics, that is Shockless equation transfer characteristics. For different VGS, you can calculate what is ID. For example, when VGS equal to 0, if you substitute here ID equal to IDSS 8 milliamperes, therefore here you will be getting a 1 point. Like that, when VGS equal to VP by 4, or that's equal to 4 by 4, that's equal to 1 minus 1 volt. And then you can calculate what is the, as per this equation, VP by 4, here it is equal to 1 minus 1 by 4 whole square, or it's equal to 3 by 4 whole square into IDSS. You will be getting 4.5 milliamperes. Like that, when VGS equal to VP by 2, you will be getting, or as per this equation, it is equal to 2 milliamperes. And when VGS equal to VP, this will become 1 minus 1 be 0, or ID will become equal to 0. Therefore, when VGS equal to VP, you will be getting it is equal to minus 4 volt, it is equal to 0. Like that one, you can plot this curve, which is called the transfer characteristics relation between VGS versus ID. Okay. Next one is that this is a fixed bias. That is why, not fixed bias, voltage divider bias. So voltage divider bias, in which two resistances R1 and R2, they are connected parallel to VDD, and this voltage, which is equal to VDD divided by R1 plus R2 into R2, that is applying to the gate. So what is that voltage? That is called VG. VG equal to 16 that voltage divided by this resistance plus this resistance into this resistance. For 16 into this, this value of this resistance, 270 kilo ohms divided by 3.1 mega plus 270 kilo. You will be getting, it is equal to 1.82 volt. This voltage equal to 1.82 volt. Therefore, once you get this VG in a voltage divider biasing, you have to draw the bias line. In order to draw the bias line, you have to apply the Kirchhoff's voltage law to this loop. What is the Kirchhoff's voltage? Applying Kirchhoff's voltage to loop, you will be getting VGS, or if you write the KVL loop here, VGS, gate to source voltage, equal to VGG minus, you will be getting, it is equal to VGG minus ID into RS. That is the drop across this one. Or this is a straight line, as you see that one, where if you get IG and ID, VGS and ID, this is a straight line in which these points for different VGS, you can find out what is the ID. And as an example, here VGS equal to VG minus ID into RS, or VG is equal to 1.82 volt minus ID into RS equal to 1.5 kilo. For different values of VGS, you can calculate what is the ID, and then you can draw a the straight line, that's called the bias line, in which you can calculate when VGS equal to 0. What is when VGS equal to 0? What is that one? When VGS equal to, substituting that one, VGS equal to 0, we will be getting, it is equal to IDRC equal to VG. From that one, you can calculate what is the ID, which is equal to 1.2 milliampere. Therefore, this is the 1.2 corresponding to VGS equal to 0. Like that one, when ID equal to 0, what is that? When ID equal to 0, you will be getting VGS equal to VD. For VD is nothing but it is equal, sorry, VGS equal to VG, not VD, VG. That is the voltage coming at this point, which is equal to 1.82 volt. Therefore, you will be getting 1.84. Once you get these 2 points, you can draw a straight line that will be touching this transfer characteristic at this point, and this point of intersection, this is the value, corresponding value of drain current at the Q point. Therefore, this is the IDQ value that will be getting as the operating value of the drain current. Continuing the same problem, bias, as I explained the previous slide, this is called the bias line, this is called the transfer characteristics, and the point of intersection is the that represent what is the VGSQ as well as this corresponding to IDQ, that is Q point drain current as well as Q point gate to source voltage, VGSQ. And from this one you can get that is equal to IDQ is equal to, it is equal to 2.4 milliamperes, and VGSQ equal to, it is equal to minus 1.8 volt. This is equal to minus 1.8 volt. Second part of the question is, what is the drain voltage? What is the voltage at this point? And in order to find out the drain voltage at this one, that is nothing but VDD minus drop across this RD, or it is equal to VDD minus ID into RD. ID, you got this operating point value of current equal to minus, sorry, it is equal to 2.4 milliamperes. Substituting that ID here, you will be getting the voltage VD equal to, you will be getting 10.24 volt. That is the voltage at this point equal to 10.24 volt. The C is that you will have to find out what is the voltage at this point. Voltage at the source side. Voltage at the source side is equal to what is the, with respect to the ground, it is the drop across RS. Drop across RS is given by ID into RS. ID is already 2.4 milliamperes and RS equal to 1.5 kilo ohms, that is equal to 3.6 volt. Therefore, this voltage equal to 3.6 volt with respect to the ground, and drain voltage is equal to 10.24 with respect to the ground. Then the voltage between the drain to source is equal to whatever this voltage with respect to ground minus whatever the voltage with respect to ground, or VD minus VS, that will be getting, it is equal to VD minus VS, same thing, VD minus VS, that is equal to 6.64 volt, or it can be found out by this equation also, VDD minus drop across this one and drop across this one. Then you will be getting what is the drain to source voltage at the operating point. Therefore, this is the VDSQ, and this is IDQ, and this is VGSQ, and these are VD and voltage at the drain and voltage at the source, VD and VS. Therefore, this is a voltage divider biasing technique, in which first you will be drawing the transfer characteristics, then you will be drawing the bias line, and the point of intersection is the operating point corresponding IDQ and VGSQ. From this value of IDQ, from the output equation, you can calculate what is the drain to source voltage at the operating point, or VDSQ.